Have jokes for next time, in case I ask you. Right, so we are working on essentially correlation. Correlation is just the name we give to data that is in linear format. And when you have data that's nice and linear, there is a unique line with many names, but one of the names is the regression line, and that's probably going to be the term I'll use most. But you remember yesterday we had other names like least square fit. I kind of like the name best fitting line, but whatever. So we have a regression line, and I'm going to give you a story behind this, but let's just remind you of some names. Isn't the x-axis called the explanatory variable, and the y-axis is called the response variable? And this one is another one of those area of a house and what it's sold for, right? So imagine this is the area of a house and what it ended up selling for. Not putting the numbers in, you don't need them to get the gist of it. And here we have the regression equation. It's basically, it's y equals, and I'm doing it as 55,000 plus 126 times the area. So if you want to find the predicted price of a house in this particular place, you would start with 55,000 and then you'd add 126 times its area, right? So you might get a question like, someone has a house that's 2,500 square feet, and they'd like to know a predicted price, what it would probably sell for, right? So I would go to the guy and say, oh, okay, I'm going to sell my house. What do you think I could get for it? And he looks at the comps, and that's what he got. He got this equation, right? It's all done through salt. And if you want to do the predicted price, then you'd go 55,000 plus 126 times the area. It's a very nice formula. Oops. And calculator takes over, thank goodness. So 55, 3,000 plus 126 times 2,500. And in this particular situation, you would say to that person, your house is probably going to be selling for about 370, right? Now, we already know that that is not guaranteed. Would you agree that you're not going to get every single house that is 2,500 square feet, even if it's in the same street? Isn't there going to be some wiggle room here, right? Maybe it's got a better view. Maybe it's got, better fridge, whatever. Maybe it's painted in a color that nobody really likes, and they're knowing they're going to have to spend money to paint it. That bright orange was not a good idea. You're going to spend money. Whatever it is, they're not the same. But this is a predicted price, right? It's going to be probably very close to that. And that's cool. Now, let's say that same person actually did, sell their house. And the real price that it sold for was 372,000. I would be very happy with that model. Would you agree that it predicted an answer that was dead close to reality, right? Now, what that might look like is that if you can pretend for a minute that that there was 2,500, that number there is the 370,000, right? Imagine up and along, right? But the dot that we got was just a little bit higher. Agree? It's just a little bit higher up than that. Not by much, but enough. And we have a name for the difference between those two. A name that you probably should use is error, but we use a word called residual, which is essentially the same thing. And the residual, you get it by taking the real price, whatever it is, and you subtract the predicted price. In this case, 372,000, take away 370,000. And in this case, it was a positive 2,000. Do you think it's possible to get a negative number for the residual. Yeah, I agree with you. Somebody's nodding their head. What would that mean if the residual was negative 2,000? In English, what would it mean?
The predicted price was more than the real price.
Yeah, you sold it for $2,000 less, right? That's all it would mean. And if the residual was zero, didn't you nail it, right? You predicted a certain price, and that's actually what it ended up selling for. So residuals are just really the difference between the real price, take away the predicted price. And we want these numbers to be small, don't we? Because if we have small residuals, doesn't this mean that the model, the equation of the line, is good at predicting the price of the house? That makes sense? If the residuals that you get when you use the model are small numbers, it's a good model. If I did a different model and I was getting residuals of 90,000 and 100,000 and minus 500,000, wouldn't I be really worried about using that formula, the model, to predict the price of any house, right? Not a good model. So how do we tell if we have got a good model? The best measure is the R value. Here are 3 R values that you might get from a set of data. Based on my picture here, I'm pretty sure that the one we got was 0.93. Would you agree those data points are really close to being linear? So if you have an R value that is very close to 1 or negative 1, you know that you've got a good model, right? 0.75, not so good, but it'll work a lot of the time. And 0.3, just guess a number, because you're probably going to be just as likely to get it right as anyone else. Can you see strong, moderate, and weak, right? Now, there's another guy that we also use called R squared. And R squared is an interesting name for something, but it is actually quite helpful. R squared is just the correlation coefficient R squared. So I'll take these answers and try and show you what it looks like. I'm going to round them off a little bit, but that's just to make them easier to work with. R squared right now are decimals. They are almost always converted into percentages because they kind of make more sense when you see them as percentages. And a very rule of thumb way of looking at them is the R squared will tell you what percentage of the time your model, right, your equation, will give you the same answer as the real value. In other words, 86% of the time, this thing here is going to be darn close to being the same answer as the one you got. So if you were saying, look, 86% of the time, I'm going to be right. You know, if you consider right, you know, plus or minus 2,000 or 3,000. 86% of the time I'm going to be right. Do you see in this one, it's just a little bit over half the time you're going to be bang on. And the other half of the time you could be, you know, 10,000, 20,000 out. In this case here, would you agree almost all the time you're going to be wrong, right? Because if you're 9% right, isn't there an 81% chance that you're miles away? And so R squared is very often used as a measure of how good your model is, right? So you can use that number or square it to get a guy called R squared and turn that into percent. Are you okay with that way of measuring it? You will see in textbooks that this, another way of looking at this is they say that 86% of the variation is accounted for in the model. And that just means that 86% of the data points will fit on that line or darn close to it. Any questions so far? So
R is the correlation coefficient, right?
correct. R is the correlation coefficient. That's its name. I don't think this particular book uses it, but R squared is sometimes called the coefficient of determination. In case you watch a video and they talk about a coefficient of determination, they just mean R squared, in case you're wondering. And almost always they turn it into a percentage. So R is always a decimal, right? You never do anything except decimals. But R squared is very often, if not always, going to be written as a percentage. So they measure different things, they measure similar things, but in a different way, right? So far, so good. Right now, I've got a little hit list of things I want to make sure I cover. So let me go and look at it. If I can find it again. There. Paper wants to stick for some reason today. So we've talked about the equations of that, and we've also now talked about them. I'll come back to that. Let's look at our formula again. The predicted price of the house is 55,000 plus 126 times the area. Now, if I write down y equals 55,000 plus 126x, so you think of that as the y and this is the x. If I write it down more the way you would do it in algebra, right? Isn't this number here, right, the slope of the line? And isn't this number here the y-intercept? Can you remember those two terms? Slope of a line, right? 126 would be really steep, right? It's rise over run. And y-intercept to do that. So if you think about what that would look like, that number where it crosses the y-axis would be 55,000. And then the slope of the line, rise over run, would be 126. We can actually, in some questions, predict or put a meaning to what these two things are doing. Let's talk about what the slope tells us. The slope says that y value will increase by whatever the slope is, by the slope for every one increase in x. So if x gets one bigger, the y value will increase by another 126. So you imagine you went a long one, the price would go up 126. Does that make sense? Now, the y-intercept is the value of y when x is equal to 0. So that again, Cody?
Slope for every one increase in?
Yeah, increase in x.
Oh, increase in x.
Right, so for every, if you take the x and you increase it, this is x, right? And you increase it by 1, right? You make it 1 bigger. The y value, which is this guy,
Goes up 126.
goes up. Right. Now, in the context of the story that I've got, right, this guy back down again, the predicted price of the house is 55,000 plus 126 times the area. The slope in this question is 126, and the units are dollars. So it's $126, right? That's what the slope is. Now that has a meaning. In other words, in the context of this question, every time you add 1 square foot, the price of the house goes up by $126. If you know anything about houses, or you're interested in buying a house, or in the past you've done that, one of the things that you very often look at is the price per square foot. I mean, isn't that a very important number? Because what that's telling you is how much house you get, you know, for your money, right? So imagine I had 2 houses. I won't tell you how big they are. But house A was $300 per square foot. And house B averages out $1,000 per square foot. I can tell you right now that wherever B isn't that a very expensive place to buy a house? Right? $1,000 a square foot. So the slope, this number here, is basically telling you what every extra square foot of house will cost you. So if I want to get a house, I don't know, 100 square feet bigger than the last one I looked at, wouldn't I have to pay 100 of those, which is what, 12,600 extra to get that 100 square feet? Now, if you went to New York, it probably would be that number. Wouldn't some of the places in New York be $1,000 a square foot? Probably in California for that reason. I think the going rate in where we are is about $200 a square foot. I think that's what the going rate in Washington is. Now, the y-intercept is 55,000. Again, it's dollars. Now, if you put an area of 0, because X is the area, that disappears, right? And you're just left with 55,000. Sometimes that doesn't have any meaning, but it does in this situation. What do you think you are buying if you try to buy a house whose area was 0? I know it sounds silly, but think about what you would be buying in an area if the house had 0 square foot.
I mean, you could be buying a singularity, although which
No, we won't go there.
I
Buying
mean, I guess
land,
it would be worth like a 55 per
Well, 55,000.
Could you be buying the land?
It is. You're just buying the land. Does that make sense? That even if there's no house, isn't a plot of land going to cost you some money? So, and there, it depends on where they are. Aren't there still places in Bremerton you can go where there's a plot of land, right? You can still build on it, right? If you wanted to. In this particular model, in this area, if you could find a plot of land, it's probably going to cost you 55,000, right? So in this case, that would be the cost of the land. So we can get an awful lot out of this formula. Not only can we use it to predict how much a particular house would sell for, or how much it would cost to buy a 2,000 square foot house. Don't I know that the price per square foot is $126? And then don't I also know that in this case, because it's the y-intercept, that the land is probably going to cost you, for a plot of land, $55,000. Now, next
well, that
one.
wouldn't matter if however much house A or B costed per square foot, if the area is 0, the land would cost the same.
Yeah. Now you could imagine somebody buying a land and building a single, a ranch, and somebody buying a same plot of land and building a 3-story house in it, if they were allowed to. Wouldn't those 2 houses cost a different amount of money? But wouldn't the land that they used to buy, to build it, would still be 55,000, right? Right. So let's look at another one, and this time we are going to do this formula. The predicted age that you are going to live to is 85 take away 1.5 times the number of cigarettes you smoke per day. Right? So the predicted age of a person is 85, take away 1.5 times the number of cigarettes that they smoke per day, right? So we've got a regression model. And where did they get that? Can you imagine that a doctor collected data on the age at which their patients died? And they also found out, well, how many cigarettes do you smoke a day? And it says, oh, I'm a 4 cigarettes, or I smoke 20 a day, whatever it might be, right? They could collect that data and it was linear, and this is what you got. Now, if you plotted it, the number of cigarettes would be, right, along the explanatory variable, and the age would be the vertical. And you can tell that it's negative and it's going down the way. Agreed? And wouldn't that make sense that if you smoke a lot of cigarettes, you probably won't live as long, right? So everything matches. So I could use this to do the usual question. So the first question you might be asked is, if someone smokes 6 cigarettes a day, what age do you predict they're going to live to? Well, their predicted age is 85, take away 1.5 times 10, and that's 85, take away 15, and that is 70. So you would say, if you smoke 10 cigarettes a day, you know, in your adult life, and you're probably on average going to live to 70. Now, that's a predicted age. It doesn't mean that when you're having your 70th birthday, you're not going to make it to the end of the day, right? You're not just going to, it's not that precise. Isn't this a predicted value? You may live to your 90, you may die when you're 40, but on average, right, you'll probably live to your 70 if this was a good model. You could be asked to explain what the y-intercept, which is 85, is telling you. In the context of this story, the y-intercept is 85, right? What is that telling you in this model?
That's the average life
definitely
expectancy for a healthy person.
For someone who doesn't smoke cigarettes, right? Is that what you're
Right.
thinking, Cody? Right? That's bang
Yeah.
on. Yeah, it's the predicted age of someone who doesn't smoke cigarettes. Have you ever read or heard on the TV or the radio or whatever, people saying things like, you know, every cigarette you smoke takes 6 months off your life? You ever heard phrases like that? For every, you know, every whatever it is, they're basically telling you this. For instance, in this case here, isn't the slope negative 1.5? Great, it's negative. And in English, that would mean for every extra cigarette you smoke, your life expectancy, right, which is your predicted age, will decrease by 1.5 years. Now, if these are just numbers I picked out of my head, I know that the gist is true. Like 85 is not bad, actually, is about the average age, but it might be in reality nothing 0.9, but it might also be 2.1. I don't know the specifics. You could go looking for it. But if someone tells you the information in this way, isn't that kind of more likely to put you off cigarette smoking, right? If I say for every cigarette you smoke, you're going to knock 1.5 years off your life, right? That might get your attention, right? We cool? Now I'm going to show you things that you cannot do with models, regression lines. The type of thing that I was doing here, right, when I predicted your age when you smoked 10 cigarettes, that's okay. If you want to find the jargon for that, when we do things like that, we call that interpreting. I'm trying to get the word interpolation. There we are. So if I use the model to figure out how long somebody who smokes 20 cigarettes or none or 4 cigarettes, right? And I use this formula, that's okay. Now I'm going to do something really stupid. I'm going to find the predicted age of someone who smoked 50 cigarettes a day. Well, the formula is 85, take away 1.5 times 50 cigarettes a day. And that's 8.5, take away 75, and that is 10. Now, there's no way that is true, because isn't that saying that if you smoke 50 cigarettes a day, you're going to die roughly by the age of 10? Well, you're not even smoking cigarettes at 10. You see, it doesn't make sense. And couldn't I make that into 100, in which case you would die at negative 30, right? 30 years before you were born, the predicted age. And what is happening here is that, first, let me give you the fancy name for it. We call this extrapolation. When you collected the data on cigarette smokers, you would probably be collecting data maybe from 0 to, well, let's say 20 cigarettes a day, right? Let's suppose that's where your data comes from. If you
What's the difference? What's the difference from the top equation to the bottom equation?
The equations themselves are the same, but in the top one, I'm using a number that's inside the range of the data that was collected. So if you only collected data on how long people lived who smoked 0 up to 20 cigarettes, it's okay to use it on a 10. It's not okay to use it as 50, because extrapolation is using it, you know, for values of X over here where there is no data. And when you're doing that, you're making an assumption that this pattern continues forever, right? And that is a very, very dangerous assumption to make, right? If you are not careful, then people will use the model for numbers they should never have used it for. Would you agree that was a bad number to use this model, right? 0 up to 20, great model, but don't use it for, you know, 60 cigarettes a day or any number. In fact, probably shouldn't even use it for 30 cigarettes a day. You agree that the data stopped at 20, right? The reason for that is, couldn't the data, if you did collect it, instead of being a nice straight line, well, it starts off being a nice straight line, but then could it become curvilinear? In other words, once you start smoking 30 cigarettes or more, it really doesn't affect how long you're going to live, aren't you? You're probably still going to die at 50, but aren't you going to die at 50 smoking 100 cigarettes a day, or die at 50 smoking 20, 30 cigarettes a day, right? There's a kind of point of it doesn't matter anymore, right? So be careful of extrapolation. So if you ever put in a number and the answer is clearly stupid, right? That doesn't make sense. It's probably because you've used a value that was outside the range of the data that was collected. So in here it was 0 to 20. Okay. If you want to do it, you're allowed to, you'll get good results. Interpolation. You're interpreting the results. Extrapolation, you're doing it outside of those results. So that is one of the issues that you have to be careful of. The next one is called this. Causation is not, oops, wrong way around, sorry. Correlation, there we go, is not causation. This is a phrase that people in statistics use a lot because people do this far too many times. When I say correlation is not the same as causation, let me give you an example. This is a true example. The numbers aren't quite right, but the idea is. if you go to countries in the world and you find out the average number of televisions in a household. So televisions count as TV monitors, right? Tablets, computer monitors, right? Anything that's got a picture, right? So TV is a kind of generic one, right? So if you went into an American house, if I went into, I'm not going to, but I went into Sydney's house, she might have 4, right? Like she's got 2 TVs, she's got a tablet, and she's got a desktop, right? You've got 4, right? So 0, 1, 2, 3, 4, 5. And then, so this is the average number of TVs in a household for each country. And then you have their life expectancy. And you will find this is what you get. The average number of TVs is very closely related to how long people live. So that one there might be America, right? And, you know, let's say that's 88, way down here, it's 70. And you look at that data and you get a nice linear straight line, right? And then you can make the big mistake. Since there is an obvious connection between the number of televisions that people on average own and how long they live for, that number of TVs that you own make you live longer. In other words, TV causes you to live longer. Do you see? Would you agree that's a stupid connection? I mean, it's a nice correlation, would you agree? Straight line, perfect. Great data for predicting. That doesn't mean TVs make you live longer. If that was the case, wouldn't America, instead of sending lots of money and medicine and food to countries that have a low standard, right? People are dying and not living long. Wouldn't we stop doing that and just send them televisions? I mean, if that was true, right? You see how silly it is. So what is the connection? What are we saying when we see this? Why is it a nice straight line? Because there must be a reason. But it's not how many TVs you own, not directly.
I was saying, probably one of the income and also how technological diffusion, where people are able to get modern technology with relative ease.
So in fact, what you're saying is correct. I'll just put it into one word. Isn't it measuring the wealth of a country?
Mm.
Won't wealthy countries in general have lots of TVs because people can afford to buy them? And when you're a wealthy country, it tends to go, mostly at least, don't you tend to have more doctors, more healthcare, live in better housing, have enough food, all the kind of cool things that go with having, you know, a reasonable standard of living. And wealthy countries have lots of those things. Now, if you're in a poor country, won't there be very few televisions, lower food quality, maybe not good housing, certainly not a lot of doctors and hospitals and medicine are hard to come by and are probably beyond the, you know, what they can afford. And doesn't that have a direct effect on how long you live? So you cannot say because this is a straight line, the X is causing Y. That's the big mistake that people make. They look at that and they say X is causing Y. Technically, what's happening isn't that there's another variable, wealth. And really, I should change this to, I don't know, the GPA of a country, right? How much each person on average makes. And I would get a very similar result. So we have got to be careful of that mistake. So the two major mistakes that get made are picking a number that you shouldn't, right? Extrapolation and getting an answer that's silly. Or making the assumption that because the data is really good, the X is causing Y. There may be another. We even have a name for it. See the real answer? It's a hidden variable. It's called a lurking variable. I like that name. Isn't a lurking means you're hiding in the corner, right? You're hidden from sight. So a lurking
Lurking?
variable, lurking, L-U-R-K-I-N-G, lurking. So that can be a British word. That's an American word. Do you use it much? Yeah, okay, so it's a good one. And so the lurking variable here would be probably the wealth. Are we good?
But I think lurking's more like creeping around, being sneaky.
Yeah, well, I think that still works. Isn't wealth creeping around and being sneaky? And all you see is TV, but there's a little sneaky thing hiding behind it that's a real culprit, right? The one that's doing all the nasties, all the good things. Okay, let's return back to what questions would look like. This is a version of question 9. The average weight of someone. So I'm going to put my little predictor on it. The average weight is negative 250 plus 6 times their height. That's fine. And the first question, A, says, suppose that a man in this age group is 79 inches tall. So they're saying it's okay to use 79. Use this regression equation to predict the weight of that individual. So the predicted weight, because I don't have to write that all the time, is negative 250, 6 times the guy's height, which is 79 inches. So I'll go to my calculator and I'll do negative 250 and I'll add 6 times 79. And according to this, he would probably weigh about 224 pounds. Okay. Now, question B would ask us, suppose that this person actual weight, right? So his real weight wasn't 224 pounds, but was 230 pounds. And they ask you to find the residual. So, are we comfortable about real takeaway predicted? In this case, I know we keep getting positive numbers, but can you trust me that you are allowed to get negative numbers? We just haven't found a question with it armed yet. That's a pretty standard one, okay? Now, in question 10, there is a scar plot. I won't give you the gist of it, but we've seen this one before. Along this axis here, it's the percentage of people who took the SAT in a state. And this vertical one was their SAT score. And you remember the dots kind of went down the way. Very roughly, right? It wasn't a great fit, but it went like that. They are telling you here that they are telling us that the slope of this line is negative 1.11. So if you can imagine, I drew the best fitting line, right, the regression line. The slope of that line happens to be negative 0.11, which is fine. So they then give you a choice of what does that mean? Well, for every 1% more who take an SAT, right? Basically, if you increase the X by 1, what will happen to the SAT score? So for every X, what will happen to the Y? Every X goes down, right? So the SAT will decrease by 1.11. And they give you 5 sentences and one of them means that. You pick the one that means that. And that one's pretty straightforward. I won't do that one. Oh, I haven't talked about deterministic, right, and statistic. There are two types of situations that we will encounter when we collect data. And I'm trying to get back to my front page. Oh, it's over here. One is called deterministic formula, and the other is called a statistical formula. Right, statistical formula is the one that we by far are going to be doing. Isn't that the one where you've got a scar plot and you do the best fitting line, right? That is a statistical formula. Isn't that basically created from the data, right? You collected 500 points, plotted them, you drew a straight line, right? If I went and got someone else to collect another 500 people, couldn't your answer be a little bit different from mine, because the people you pick might be a little bit different in some way than I do? Because that's just the variation of life, right? A deterministic formula would be one where there is 100% fit. So I'm trying to think of one. God, there must be an easy one in the world to do. Yeah, here we go. If you do y equals 32 plus 1.8x, but I tell you that y is degrees in Fahrenheit, and I tell you x is the degree in centigrade. Has anybody seen that formula for converting centigrade to Fahrenheit? No. Right, this is how you do it, right? If you go to Europe, everywhere, I can't think anywhere where it's an exception, you don't get it's going to be 80 degrees today. What you'll get is it's going to be 20 degrees centigrade, right? Or 25 degrees centigrade. And this is the formula that you would use. So for instance, if it was 20 degrees centigrade, you would do this calculation. And you would get, oh, you mean it's 68 degrees. Now I know what you're talking about. It's not scorching, but it's okay. If you have done physics, I'm pretty sure you've done centigrade. And if you've done chemistry, I'm pretty sure you've done centigrade. In fact, in a lot of the sciences, don't you use centigrade rather than Fahrenheit when you talk about everything, right? So that is a deterministic formula. I'm not saying that if the 20 degrees is kind of probably close to 68, no, sometimes it'll be a little bit more than 68 and sometimes it's not. Isn't 20 degrees exactly 68? And it's a perfect fit. So that's what a deterministic model looks like. It determines exactly what the answer is. Whereas if I went and said to you, the predicted price of a house was 55,000 plus 196 times the area. Isn't that a statistical formula? Wasn't that based on data? And any answer I get, isn't it only a rough guide to what the real value might be? And hopefully it'll be close to it, but not exactly it. Woody?
So does that little pyramid over the price, does that mean?
Yeah. That is for the word predicted.
Predicted.
So you read that out as predicted price. I know that the textbook may not put that little hat above it, but it's a good idea to do it because that's what virtually everybody else does. So this just a little idiosyncrasy of WebAssign. Right, so are you comfortable the difference between a deterministic formula and a statistical formula, right? You still use them the same way, don't you? Plug in the number and get the answer, right? So it's not like they do much with that, except if you do a deterministic one, won't the residuals all be zero?
Yeah, I was gonna ask, so deterministic, that won't even have a residual, would it?
Well, the residual would be zero, so I guess it doesn't have one, or the residual is zero, whichever way you want to phrase that. But in a statistical one, won't you get numbers in your residuals, right? Some are going to be a little bit big, some are going to be a little bit small.
So if statistical is predicted and then deterministic is 100% fact?
Yeah. Yeah. So if you did deterministic one, wouldn't your formula look like a whole set of dots all in a perfect straight line because it's a perfect fit? Whereas if you did a statistical one, wouldn't there be a little bit of wiggle room, even if it was a good fit? You see the difference between the two. We almost exclusively in statistics deal with these guys, right? These are for sciences, right? Sciences can do deterministic, right? They've got formula that tell you exactly what the answer should be. In statistics, we develop formulas that predict, as best we can at least, what the answer should be. Okay. Oh, shooting space. I get so caught up, I forget the time. Last name, everyone. We're finished for today. Bye-bye for now. I'll see you tomorrow. We learned some cool stuff today. We learned that TVs don't make you live longer. Right?
You know what's interesting? The correlation versus causation was actually brought up first to me in my human anatomy class.
Oh, what were they talking about? Can you remember the details?
It was similar to like what you were saying about cigarettes and them not living longer, just because we can find something happening in the human body in one person, and like having like this example of like something that they're doing in their life doesn't mean that what they're doing in their life is causing what's going on in their body, like for them to get like ulcers and stuff like that.
Yeah, so you could say like, I don't know, people who drink a lot of milk, or somebody that drinks a lot of milk, and then you find out that those people have high diabetes. It doesn't mean drinking milk is causing high diabetes.
They actually used a similar one. They were like, people who drink more milk tend to have more calcium in their body, when actually they might have, it was different. And also another one that they used was, oh, what was it? The biggest one that they used was like, oh, it just slipped my mind. I was just thinking about it too.
Well, it's nice when other people do what we do, and you can say, oh, so that's why they use
that's what it was. The ulcers, like just because someone was more stressed out in their life, they had more ulcers going on, when in reality, that's the whole thing that they had with doctors were like, oh, you need to have less stress so you don't get ulcers. It wasn't, the stress wasn't causing ulcers. It was actually a bacteria
that caused ulcers. I am old enough to remember when they didn't know that. And they used to say things like spicy food, drinking too much lager, and stress. So if you had ulcers and you went to your doctor, they would say, well, you know, it's a lifestyle thing. You know, ulcers are brought about by stress, or eating too much spicy food, or, you know, taking, you know, lager, acidic, anything that was acidic. They kind of, well, that makes sense. You know, acidic burns holes in your stomach, causes acid, you know, whatever you want to call it, right? And then it was, they found out it was just a bacteria. And once you find out what the real reason is, you can then fix it. Because if you think it's drinking too much lager, they can stop drinking lager, but it doesn't cure the ulcers, you know? You're not fixing the problem. So yeah, it's very important that we know the reason for something, and not, you know, drinking lager. People who drink a lot of lager have a lot of acids. Now, you know, I could do it the other way around. If you were in a lot of pain, right? You might drink a lot of alcohol because it deadens the pain. And so people will say, oh, people who drink a lot of alcohol have a lot of pain. Drinking alcohol is causing pain.